And in this problem statement, we're given that we have a CSTR that is 100 liters, and we aren't really given any information about the feed characteristics, and so we'll leave those unspecified as some entrance molar flow rate and entrance concentration. But we do know that in this reactor we achieve a conversion of 75%. And we also know that eventually in this problem we're going to want to add a 100 liter plug flow reactor in series with this CSTR and have it either upstream or downstream of the CSTR, whatever is going to lead to the higher conversion in this case. An advantage of this series process is that we know that the feed characteristics of the overall process are fixed. All right, so we are going to be feeding initially, before any conversion happens, a certain molar flow rate and concentration, and we can use the conversion to track in either reactor how the molar flow rate and concentration will change as a function of going through these two different reactors. All right, but for now we're going to start by just considering a single reactor before we show how this can be an advantage that we have this constant inlet molar flow rate and molar concentration to our total process. All right, we don't know what those molar flow rates and concentrations are, and as we'll see, we don't know what maybe another key variable is in this process. So we want to try to set up a material balance around this CSTR in order to be able to solve for some of those variables. And the classic form of the material balance that we have in terms of conversion is the following. All right, and we can fill in some information here. So the volume divided by the inlet molar flow rate of our limiting reactant A is equal to the conversion in the reactor over the rate at the exit conditions. And so the conversion is given as 75%. All right, the rate we know is equal to kCA0 squared times 1 minus the conversion squared. And so we will have a rate constant here that we don't know the value of, but we'll just put it in there for now. And then we have a 1 minus the conversion at the exit conditions, and that conversion at the exit is 75%. And so then we just need to square that. So we don't know some of these values. We do know the volume, but for now I won't even bother to plug in actually what the volume is. And instead I'm going to just lump all of the variables that are in that equation over here. All right, and if we solve for the value of 0.75 over 1 minus 0.75 squared, then we just get that the value of these lumped parameters is equal to 12. And so this is a dimensionless quantity, these lumped parameters. As we'll see later, this dimensionless quantity is called the Domkohler number, and it's a characteristic of a reactor that can be used to sort of tell us something about how well the reactor performs. All right, for now, though, we're just going to use this Domkohler number to tell us something about the relative values of these different constants in our reaction system, and realize that when we add in a plug flow reactor, it's not going to affect any of these terms. So the rate constant K is just a function of the reaction that's being run, and that's not being changed when we use a plug flow reactor. The volume is 100 liters for both types of reactors. And again, our feed to our total process, FA0 and CA0, is not going to change when we add in another plug flow reactor, either upstream or downstream of the CSTR. Our initial feeds to the individual reactors can change, but we can actually take that into account just by having the reactants enter at a conversion greater than 0, as we'll show in just a minute. Now let's start with the case where we want to place the PFR second in the series. So we're going to pipe it up so that the fluid with a conversion of 75% enters the PFR, and we want to know what final conversion we're going to get out of the PFR. And we'll just evaluate both possibilities for placing the plug flow reactor either upstream or downstream of the CSTR. In the case of a plug flow reactor, we have the following for our design equation, where it looks fairly similar to a CSTR, but it's differential in nature because of the fact that the reaction rate changes down the length of the reactor, as we talked about previously. All right, here, to take into account the fact that the fluid is not entering at its feed flow rate and composition for component A, we want to take into account the fact that it enters at a conversion already of 75%. And so we're going to be integrating from an initial conversion of 75% up to some final conversion x2 that we don't know. Right, and this takes care of the fact that the entering flow rate into the PFR is not at these initial concentrations before the reaction began, but are at conditions where the conversion is 75% already. And this takes it into account in the material balance. All right, now we can just plug in for what the reaction rate should be. Here we see that we have these constants again. And so we can take these constants out. All right, the rate constant and the initial concentrations are not functions of conversion. And so we can pull them out of the integral and multiply both sides of the equation by those quantities. And we end up with, again, our Domkohler number. And we've just said that it's going to be the same for both the PFR and CSTR, which means it has a value of 12. And so now we can just solve for the value of x2 that makes this equation hold. When we do the integration, we get the terms over to the right. We can then solve for the value of x2, and the conversion that we get from placing the PFR downstream of our CSTR is a conversion of about 93.8%. Now let's see what happens when we place the PFR actually upstream of the CSTR. Okay, in this case, we're going to have flow coming into a PFR. It will achieve some conversion, intermediate conversion x1 that we don't know. We expect it to be greater than 75% because we have the same volume PFR as we had CSTR before, and PFRs are inherently more efficient for positive order reactions, as we'll see. All right, and then whatever this conversion is, the fluid will enter the CSTR at that conversion and be converted to some final conversion x2 that we also need to solve for. All right, again, our approach is going to be to set up the material balances for each reactor in the series, and so we'll do that for the PFR first. This is the general form of our design equation for a PFR, just as above. The only thing that's changed is our integration limits. Now we're starting at a conversion of 0 and going up to the intermediate conversion x1. We again get this function for the rate shown here. These terms are constant again, so we're going to get a very similar looking expression here, where we get the kCA naught squared that we can pull out of the integral and multiply both sides by that kCA naught squared. And so we again get our Domkohler number. All these values are constant, just the same values as they were at the start of the problem. So this number is equal to 12. And now we just need to solve for x1. And when we do that and apply the new integration limits, we get 1 over 1 minus x1 and minus 1 is equal to 12. And when we solve for x1, that gives us a value of about 92.3%. So as expected, we do get a significantly higher conversion by placing that more efficient PFR at the front. All right, now we need to solve the material balance around the second reactor, the CSTR. Again, here is our design equation. All right, in this case, because we're not entering at a conversion of 0, we need to have x2 minus x1 for our material balance to work in the numerator of the right-hand side of the equation. And then the reaction rate is going to be occurring at the outlet conditions of the CSTR, which is at the final conversion that we're going to need to solve for in this problem. All right, again, we can multiply both sides of the equation by kCA naught squared. And we get our Domkohler number again, so we know that this value has to be equal to 12. We also know that the value of x1 is equal to 0.923, and so we can just plug that directly into our equation. And our only unknown in this case is now x2, and we can solve for the value of x2 to be equal to about 95.1%. And so we see that in this second configuration, where we place the PFR first and the CSTR second, we get a higher conversion from our total process of 95.1%. And so this is the configuration that we should use if we're trying to maximize the conversion. All right, the reason why this is a better configuration to use in the case of a second order reaction that we have here, so here we have a dependence on the concentration that's second order. All right, and so that means that we get a bigger advantage because the rate in a plug flow reactor starts off at the inlet concentration, and the rate is proportional to that concentration squared. All right, we get a bigger advantage from having the plug flow reactor first because the rate has a very strong dependence on concentration, and we therefore are having the concentration be as high as possible in the plug flow reactor by having it before we have the CSTR. For a second order reaction, it's desirable to try to maximize the rate by maximizing concentration, and we get the maximal concentration at the inlet conditions. And so we want to have the PFR see the reacting fluid at those inlet conditions so that we can take advantage of the high concentration and therefore high rate that we're going to get for these second-order reaction systems.